So what we are going to learn in this module is how to test the difference between means of more than two samples involving more than one treatment or characteristic. We would learn about two-way ANOVA. We would also like to evaluate simple problems involving testing for difference in sample means due to two or more characteristics, and also learn about how to find out which of the two means are not similar or equal to other means. The background or basics about two-way ANOVA. Earlier, we have learned to compare the means of two populations using the test of hypothesis, or more precisely, the t-test for the difference between means. Now we also know that if the sample mean of more than two populations is to be compared, then t-test is a cumbersome procedure. A better alternative is the ANOVA technique. ANOVA, as you might know, stands for analysis of variance, that helps us to test the difference due to same factors in means of more than two populations at a same time. We know this is called one-way ANOVA. Since this method examines sample variances to establish whether difference in population means exists, it is known as the analysis of variance method. Sometimes the samples or the experimental units are influenced by more than one factor. If we wish to study the impact separately, a two-way ANOVA therefore becomes particularly useful. The assumptions for the application of this two-way ANOVA, however, are the same as those we have studied in our earlier module on one-way ANOVA. But let me repeat these assumptions. What are these assumptions? The assumptions are that all populations under consideration are assumed to be normal, the samples chosen are independent, and the treatment effects or effects of blocks are additive in nature. Thus, the two-way ANOVA is nothing but an extension of one-way ANOVA, where variation between rows and columns is studied simultaneously. So, what is two-way ANOVA? Let's begin with the concept of it. Sometimes one factor or treatment may not be sufficient to compare population means. For example, in our fertilizer treatment, we were trying to study whether three different types of fertilizers A, B and C had the same impact on crop yield of a unit of land. All of us understand that besides the fertilizer quality, there could be several factors that may influence crop yield. It could be fertility of land, rainfall received by it, quality of seeds used, and probability of the education awareness, or in other words, the ability of farmers on the selected plots of land. If we have to study two factors at a time, then we need to develop a two-way ANOVA table. Here we group our experimental units or samples not only on the basis of a treatment but also on the basis of another factor. For better understanding, let us take the same example as taken in our earlier module on one-way ANOVA. So let's assume that there are plots of land subject to three different types of fertilizer treatment A, B and C. In a two-way ANOVA, we also categorize the plots on the basis of another factor, say farmer ability. We group our experimental units, or known as samples or plots of land, on the basis of those owned by farmers with low, moderate and high ability, or let's say high awareness. In other words, we are not just grouping our samples column wise, which means on the basis of treatments or group wise, but also row wise, which has levels of farmers' ability. Such a classification will not only help us study whether application of different type of fertilizers has any impact on average crop yield, like in our previous one-way ANOVA, but also whether farmers' ability influences crop productivity or not. Farmer ability is often called a blocking variable. In our example, we have 3 blocks, one for each level of farmer's ability. Such a design is known as a randomized blocks design. The randomness arises because we randomly select one farmer with low ability and working on land that is treated with fertilizer A, and so on. Now this process is repeated for each category of farmer's ability and for each fertilizer type. The form of two-way ANOVA model will be as below. We have crop yield per acre. On one hand or one side we have the treatment and we have the block in the other side. So in blocks we have the farmer's ability, low, which can be denoted as 1, moderate 2, high 3, which is in terms of rows, and we have the sum total, which is H. Then we have the treatments A, B, C up to K, can be written as 1, 2, 3 and up to K. The cell values are x11, x12, x13, x1k for low. For moderate values we have x21, x22, x23 up to x2k. For high we have x31, x32, x33 and x3k. And for H, which could be very high, etc., it is xh1, xh2, xh3, xhk. Now in this case we can say that xij is the crop yield of plot of land owned by farmer with ability I, block, and subject to fertilizer of type J, which could be known as a treatment. So we have a block I and we have a treatment J. In a generalized format we have K treatments or groups ranging from 1 to K, and we have H blocks from 1 to H. The total number of observations or observations experimental units is small k into H and is equal to capital N. In order to test the hypothesis that population means are same for all K groups or treatments, we need to calculate sample means for all treatments. So we denote xj bar equal to summation of xij of summation is over I, which ranges from 1 to H, divided by H, and J ranges from 1, 2, 3 up to K. So for each J we calculate xj bar. But if we wish to compare population means across block, we will have to calculate sample mean for each block, which is row in this case. And we can denote xbi bar, which refers to the mean of block I. And therefore x bar bi or xbi bar is equal to summation of xij over j, and j ranges from 1 to k, and this divided or in the denominator we have k. So divided by k, and the I ranges from 1 to H. As mentioned earlier, we have H blocks. Now grand mean of all observations can be calculated as x double bar and is equal to double summation of xij over I and j. I ranges from 1 to H and j ranges from 1 to k, divided by capital N. And this can also be calculated as equal to summation of xbi bar and j ranges from 1 to k divided by k, or is also equal to summation of xj bar, where I ranges from 1 to H and divided by H. In two-way ANOVA, there are 3 sources of variation, namely between treatment or groups sum of squares denoted as SSB, and this SSB is equal to H into summation of xj bar minus x double bar whole square, where j varies from 1 to k. Our second source of variation is between the blocks oblique rows sum of the squares, written as SSBL. So SSBL is equal to k into summation of xbi bar minus x double bar whole square, and the summation is over I, which ranges from 1 to H. The third source of summation or third source of variation is total sum of the squares, TSS, which is the total variation amongst all sample units and is denoted as TSS and is equal to double summation of xij bar minus x double bar whole square, where I ranges from 1 to h and j ranges from 1 to k. The fourth is the error sum of the squares, ESS, or within the group sum of the squares, SSW, and this is SSW is equal to TSS minus the in the bracket or summation of SSB plus SSBL. Like in one-way ANOVA, in two-way ANOVA also, the mean sum of the squares are obtained by dividing the sum of the squares obtained as above by the relevant degrees of freedom. As we know that if we have k treatment or groups and h blocks such that the total number of observations n, which is capital N, is equal to h into k. So degrees of freedom for total sum of the square is equal to n minus 1, degrees of freedom for SSB is equal to k minus 1, degrees of freedom for SSBL is equal to h minus 1. We also know that degrees of freedom of ESS divided by SSW is equal to degrees of freedom of TSS minus degrees of freedom of SSB minus degrees of freedom of SSBL. So it is equal to capital N minus 1 minus k minus 1 minus h minus 1, and thus is equal to n minus k minus capital H plus 1, and therefore is equal to kh minus k minus h plus 1, because we know capital N is equal to k into h, and therefore is equal to k into h minus 1 minus 1 into h minus 1. Therefore, degrees of freedom of ESS upon SSSW is equal to h minus 1 into k minus 1. The results of the two-way classification ANOVA is also or can be summarized in a tabular form below. Now, in this table form, again we have the sources of variation, we have the sum of the squares, we have again the degrees of freedom, the mean sum of the squares, which is same as sum of the squares divided by degrees of freedom, and in the end we have the F ratio. So in the rows, first we have the between groups variation, then we have the between blocks variation, then we have within groups sum of the squares of or error sum of the squares, and then we have the total sum of the squares in the last row. I am sure you can see that sum of the squares can be written as SSB, SSBL, SSW or SSE, and total sum of the squares. The respective degrees of freedoms are k minus 1, h minus 1, k minus 1 into h minus 1, and n minus 1 for TSS. The mean sum of the squares are now MSB is equal to SSB upon k minus 1, MSBL is now equal to SSBL upon h minus 1, MSW is equal to SSW upon k minus 1 into h minus 1. What are the F ratios? The first F ratio of between the groups is MSB upon MSW, and the second F ratio of between blocks is MSBL upon MSW. Note that we can calculate two F values by using the mean sum of the squares between groups and G, the mean sum of the squares between blocks. The ratio of MSB to MSW is used to see whether population means vary across treatment, and the second ratio between MSBL and MSW is calculated to test whether population means differ across blocks. So we can test two hypotheses with a two-way ANOVA table. That is the advantage of two-way ANOVA. So let's learn about testing of hypothesis for two-way ANOVA. The null hypothesis H0 is set up as the population means across treatments are the same, or the treatment does not cause variation in the observations over each block or oblique sample unit. The alternative hypothesis H1 now is that population means are not all same or treatment does not influence observations. Our second null hypothesis H0 is that population means across blocks or sample units are the same. And the alternative hypothesis now is that population means across blocks are not all same or block factor influences the observational value or observation values. Let's again take level of significance alpha equal to 5% or 1% and test statistics is the F ratio. We have already learned that we may have two F values, F1 MSB upon MSW and F2 as MSBL upon MSW. F1 is the calculated F value for the first set of hypotheses, and then it is compared with the F table value with K minus 1 and K minus 1 into H minus 1 degrees of freedom for numerator and denominator respectively at a chosen level of significance, which could be 5% or 1%. Similarly, F2 is the calculated F value for the second set of hypotheses and is compared with the F table value with H minus 1 and K minus 1 into H minus 1 degrees of freedom for numerator and denominator respectively at a chosen level of significance. Let's now look at the third step, which is the decision rule, which is similar. That is that if this F calculated is greater than the F tabulated or F from the tables, then we reject the null hypothesis that population means are the same across treatments. Similarly, in F2, if F2 is greater than Fh minus 1 and K minus 1 into H minus 1 and alpha, then we reject the null hypothesis that population means are the same across blocks. Let's do this learning of two-way ANOVA through an example once again so that we have clarity on how do we ultimately use a two-way ANOVA in our real world. We have an example to understand this two-way ANOVA, and which is again a similar example in an agricultural setup. Suppose it is desired to study the differences in the yields of three different varieties of wheat using three types of fertilizers. The data obtained is put in a tabular form as follows, and it is in terms of number of bushels per acre. And so we have the varieties of wheat A, B, C and fertilizers 1, 2, 3. The cell values of 86, 88, 84 in the first row belongs to fertilizers 1, and similarly 92, 91 and 92 for fertilizer 2, and for fertilizer 3 we have 75, 80 and 78 corresponding to different varieties of wheat respectively. Now test the hypothesis that population mean yields are same for all varieties of wheat. Also test that population mean yields are same for all three qualities of fertilizers, which basically means we are trying to test that fertilizer quality or the wheat quality or the wheat variety does not make any difference to the yield. What is the solution to this problem? The solution is that we again tries to find out in terms of these means and the F ratios. So let's do that. In our table, now in our last column, we have in our first row x1 bar, which is equal to 86, which is the mean of 86, 88, 84. Similarly, we have x2 bar equal to 91.63 and x3 bar equal to 77.67. In our last row corresponding to each column A, B, C, we have XA bar, XB bar and XC bar corresponding to wheat variety of A, B, C. XA bar is equal to 84.33, which is the mean of 86, 92 and 75, the three values in column corresponding to wheat variety A. And XB bar is equal to 86.33, XC bar is equal to 84.67. So we have the mean yield corresponding to each variety of wheat and in the row we have the mean yield corresponding to each fertilizer or each block. The grand mean X double bar comes out to be 85.11, which is nothing but the mean of all the cell values, which are 9 in this current example. Let's try to find out between the group sum of squares or SSB. SSB is equal to H into summation of xj bar minus x double bar whole square, where j varies from 1 to k. And therefore we get 3 into summation of xj bar minus x double bar square plus xb bar minus x double bar square plus xc bar minus x double bar square. On substituting these values, what we obtain is equal to 6.889. Similarly, as we have defined earlier, between the block sum of the squares, SSBL is defined to be equal to k into summation of xbi bar minus x double bar square, where I ranges from 1 to h. Now this is equal to 3 into x1 bar minus x double bar square plus x2 bar minus x double bar square plus x3 bar minus x double bar square. And on substitution of these values, we get the summarized value equal to 297.56. Let's now move to the third step, which is finding out the total sum of the squares, TSS. How do you find out TSS? TSS is again by definition equal to double summation of xij minus x bar or x double bar square, which is nothing but the cell values minus the mean of all these cell values and their squares and their summation over all cell values. So on substitution, you get this equal to 318.889. Let's now find out SSE or SSW, which is within the group sum of the squares or error sum of the squares. Now, as defined earlier, this is equal to TSS minus SSB minus SSBL. And if you substitute these values of 318.889 minus 6.889 minus 297.56, we obtain error sum of the squares or SSE equal to 14.44. We can place all these values in our table, which is given below, and on the basis of these substitutions we can find out the mean squares as well as the F ratios. In your second column of sum of the squares, you can see we have just substituted the values of SSB, SSBL, SSE or SSW and total sum of the squares, which are borrowed from the calculations we made just now. Now, if you look at the degrees of freedom, the degrees of freedom for between groups is equal to k minus 1 and therefore is equal to 3 minus 1 equal to 2. For between blocks, it is equal to h minus 1 and is equal to 3 minus 1 is equal to 2. The error or within groups is degrees of freedom is equal to k minus 1 into h minus 1, which is 3 minus 1 into 3 minus 1 is equal to 4. And for total sum of the squares, degrees of freedom is n minus 1 equal to 8. Now in the next columns, we have the mean squares, which are obtained from dividing the sum of the squares by the degrees of freedom, and you have the corresponding values. Let me now concentrate on the last column, which is the F ratio. The first F ratio is equal to MSB upon MSE, and what we obtain is equal to 0.9 because we have substituted the value of MSB equal to 3.444 and of MSC equal to basically 3.611. If you look at the second F ratio, it is equal to MSBL upon MSE, and this comes out to be equal to 148.78 divided by 3.611 and comes out to be 41 or approximate value of 41. Now, if you look at the null hypothesis, our null hypothesis, the first one is that population mean yields are same for all varieties of wheat, and therefore we can denote it as mu A equal to mu B equal to mu C. And the alternative hypothesis is that population mean yields are not all same. Alpha we have selected as 5%, And now if you look at the first F ratio, F1 is MSB upon MSE and is equal to 0.954. Now if we look at the tabulated value for K minus 1 and K minus 1 into H minus 1 degrees of freedom at 5% level of significance, it comes out to be 6.94. And now we find that since F1 is less than this F tabulated value, we fail to reject the null hypothesis. We hence conclude that population mean yields are the same for all varieties of wheat, which means wheat variety does not necessarily influence the crop yield. Similarly, if you look at the second hypothesis, where we have the hypothesis of population mean yields are same for all three types of fertilizers, which we are saying is mu1 is equal to mu2 is equal to mu3. In that case, you can find out that again taking alpha equal to 5% and looking at the value of F2, which is MSBL upon MSC and is equal to 41.2. Again, if you find out the F tabulated value for now H minus 1 and K minus 1 and H minus 1 degrees of freedom, at 5% level of significance, it comes out to be 6.94. Now, since we find that this F2 is greater than this tabulated value, we therefore reject the null hypothesis. That is, the population mean yields are not the same for all three types of fertilizers. It perhaps means that fertilizers do have their impact on the yields of the wheat in this particular example. Let's now understand what are the limitations of this ANOVA and what are the further tests which we can apply in this case of limitations. As mentioned earlier also, that ANOVA only tells us whether to accept or reject the null hypothesis for equal means. However, when we reject null hypothesis, ANOVA cannot tell us which of the means are not similar or equal to the others. It is possible to find this using other tests of significance. One such method used in the two-way ANOVA is the least significant difference method, which we have also discussed in a previous module on one-way ANOVA. The procedure followed for the two-way classification ANOVA is as follows. LSD, which means means of rows, is equal to the critical value of T for error, degrees of freedom, and level of significance alpha into under root of 2 mean sum of a square or sum of errors divided by number of rows. Now this can be written as T with degrees of freedom as K minus 1 into H minus 1 and alpha by 2 as the level of significance into under root of 2 MSC divided by K. If modulus of xi dot bar minus xj dot bar is greater than LST, where I is not equal to j and j is equal to 1 to h, then the ith and jth row means are said to differ significantly. The least significant difference or LST for any two columns, which means for treatments or groups, is given by LSD means of columns is equal to T with degrees of freedom K minus 1 and H minus 1 and alpha by 2 as the level of significance into under root of 2 MSC upon H. Now, if again modulus of x dot I bar minus x dot j bar is greater than LSD, where I is not equal to j and j is equal to 1 to k, then ith and jth column are said to be significantly different. So we are testing either whether the two columns are different or they differ, rows are said to differ significantly or the columns are said to differ significantly. Let's do some learning of further tests through an example. A college is considering employing fully integrated office computing system. It has shortlisted 3 alternatives A, B and C. The final choice will depend upon the system's productivity measured in output per hour. Now 5 operators are selected to work on each type of system. However, it is believed that the operator's experience is likely to influence the productivity of the systems. Therefore, operators are classified according to their level of experience from 1 to 5, a lower value indicating lesser experience. The productivity table is given as follows. So we have productivity, which is measured at output per hour, and we have the experience level of operators from 1 to 5 based on their experience and in a way, and we have the system treatments A, B, C, and the values 26, 30, 40, 40, 47, etc. are nothing but their productivity, which is output per hour. The question is, find out if there is a significant difference between systems, which means treatments productivity, or also if there is a significant difference between operators with different experience level and their productivity. If yes, which two system operator category are different? Now this is what we have to do. So what is the solution? We have in our table, in the last column and in the last row, the means of the respective rows and the respective columns. If you look at the respective row means, which are denoted as xi bar, we have 23.3, 32, 39.67, 40 and 46.34 as the means, and in the last row we have the mean denoted as xj dot or xj bar, which are the column means and are equal to 36.6, 36 and 36.2. The grand mean x double bar is equal to 36.27. Now with two-way ANOVA, the total sum of the squares is divided into between the group sum of the squares, and on substitution of these values in the formula which we have discussed earlier, and I don't want to repeat that formula, this comes out to be equal to 0.9333. Similarly, between the block sum of the squares SSBL comes out to be, on substitution of the values, equal to 936.933. And if you look at the third calculation, which is within the group sum of the squares or error sum of the sum of the squares, which is calculated from TSS minus SSB minus SSBL, it comes out to be equal to 35.067. And what is the total sum of the squares? The total sum of the squares on substitution of the values, which is obtained from our formula of double summation of xij minus x double bar square, is equal to 972.933. So if I summarize all these calculations in our two-way ANOVA table, again you can see we have the sources of variation, we have the sum of the squares, degrees of freedom, mean squares and F ratio. And we are mainly interested in the two F ratios. Look at the first F ratio, which is equal to MSB upon MSE. It is equal to 0.1065, which comes out from MSB equal to 0.47 and MSE equal to 4.38. Similarly, our second F ratio, which is equal to MSBL upon MSE, it comes out to be equal to 53.4. And I'm sure you can calculate how it comes out to be from the MSBL value of 234.23 and the MSE value of 4.38. Let's look at the two null hypotheses which we have set up. The first null hypothesis is that population mean productivity of computing systems is same, which means that mu A is equal to mu B is equal to mu C. And obviously our alternative hypothesis now is that population mean productivity is not all same. Level of significance alpha we have selected is 5%. F1 is equal to MSB upon MSC, which is equal to 0.1065. Let's now calculate the tabulated value for k minus 1 and k minus 1 into h minus 1 degrees of freedom at 5%. Now this from the table you can see comes out to be equal to 4.46. So as we find that the calculated value of 0.1065 is less than this tabulated value, we fail to reject the null hypothesis. We hence conclude that population mean productivity of computing systems are the same. Let us look at the second null hypothesis, which is that population mean productivity of all operators with different experience level is same. which means mu1 is equal to mu2 is equal to mu3 is equal to mu4 is equal to mu5, and alpha is again 5%. But now F2 is equal to MSBL upon MSE and is equal to 53.43. Again, if you look at the tabulated value for H minus 1 and in K minus 1 into H minus 1 degrees of freedom, at 5% level of significance, you find it comes out to be 3.84. Now we may see that since the calculated value is greater than the tabulated value, we reject the null hypothesis, which means that there is a significant difference in the operator's mean productivity. Now, this is what we are saying is the productivity of operators with different experience level is different. LSD, which is least significant difference to identify which treatment blocks are different. Now, that is what we can also do in this example. So, in our example, there is a difference in productivity of operators with different experience level. To identify which set of operators perform differently, we can employ our LSD technique. Let's find out from this or with the help of this LSD technique, which is nothing but means of rows for a given formula, which we have already emphasized 2-3 times, is equal to T for a degree of freedom K minus 1 into H minus 1 and alpha by 2 multiplied by under root of 2 MSE upon K. So if I substitute these values, the T value comes out to be 2.306 and the under root value comes out to be equal to 1.70. Once we multiply them together, we get 3.94. If you now find out the difference of x1 bar and x2 bar, it is 8.67, which is greater than 3.94. Similarly, the difference of or modulus difference of x1 bar minus x3 bar is also greater than 3.94. So you can keep on finding out all these differences, pairwise differences, and see which is greater and which is smaller than 3.94. From this comparison, we can conclude that performance of operators with different experience levels differ significantly, except for experience levels 1 and 5 and experience levels 3 and 5, where you find that these values are not greater than 3.94, which is our LSD value. So what have we learned from this entire module? We have learned, and let us summarize that learning, that two-way ANOVA helps to study whether there is difference in means of more than 2 samples involving 2 characteristics at a time. We have also learned and seen how population means are different or not. This method analyzes or the various sources of variation, namely within the groups or treatments, within the blocks or sample rows, and between groups errors. We have also learned, or the third learning has been, that the test statistics used here is the F ratio, which is the ratio of between the group mean sum of the squares, written as MSB, and within the group mean sum of the squares, written as MSW. The second F statistics which we have learned and have calculated is the ratio of between the blocks mean sum of the squares, written as MSBL, and within the group mean sum of the squares, written as MSW. Another learning has been that the calculated value of F is compared with critical value, which means the table value, with relevant degrees of freedom and at a particular level of significance. And again, which may be a repetition, if calculated F is greater than critical F, we reject the null hypothesis of no difference between means. And lastly, we have also learned that once we conclude that there is a significant difference between sample means, the least significant difference or LSD method helps us to identify which sample means are not equal or differ significantly.